Okay, all right. Good afternoon, everybody. So, inshallah, today we conclude our course with lots of work. Sorry about that, but this is the nature of life. All right, so today is, what class is that? Today is class 1 of week 15. All right, we finished the T model last time and all the models, and today we touch basically the amplifiers. So be ready, take notes. We have lots of things to go through. We have 3 types of MOSFET amplifiers. MOSFET amplifiers, what are they? MOSFET amplifiers, what is the type of MOSFET amplifiers? Huh? MOSFET amplifier. Yes. صح one. Yeah.
Common drain.
Common drain amplifier. What's another name for common drain amplifier? Do you know? Who knows? Common drain amplifier, raise your hand. Yes?
Current followers.
Source follower.
Very good. You were very close. So it was between you. Yeah. Was source follower. What the third one? Yes? Common gate. Very good. Now the same thing for the BJT amplifiers. So basically we will have what?
Common-Emitter.
Common-Emitter.
Common-Base.
Common-Base.
Common collector.
Common collector. Boom. Very easy. We don't need any memory. صح ولا لا? We use just common sense and everything will be fine. Very good. So this one will be what? This one.
Common-Emitter.
Why?
Because
Yeah.
the emitter is grounded.
خلاص. Bingo. That's it. So common-Emitter because it's grounded. Then this one will be
Collector.
common
Collector.
or
Emitter
Emitter
follower.
emitter follower. Very good. That's, you see how we play? It's a game, huh?
Yeah.
Emitter follower. Very good. It's written. Somebody cheated, huh? No, Sure?
Yes.
I trust you. And the last one will be
Common-Base.
common base. Very good. That's it. However, we have to remember these parameters that we talked about it last time. GM. GM, what's GM? What we call GM?
Conductance.
We explained
Transconductance.
linguistics. Transconductance. Very good. Transconductance, the BJT transconductance. And RE, which is RE. What is RE?
Emitter resistance.
Exactly. But we call it emitter resistance, but in fact it's Rin when we look at the emitter from the emitter base. When we look at the emitter, we see only RE. Okay? Alright, good. And R pi is the input resistance, Rin, when we look at the base. Okay? That's what it is. Go back to the definitions. We said that actually. Okay? So the input resistance through the emitter is Re, and the input resistance or impedance when we look at the base is R pi. Very good. And R naught.
Output
Collector.
resistance. Output resistance.
Collector.
Yeah, what's the collector? Is actually, go ahead.
The output of the current, which is in the collector.
The R naught is actually between the collector and the emitter.
Yes.
Okay, we call it the amplifier, the BJT output resistance. The BJT, not the amplifier, because the amplifier has the BJT and other stuff. But this is only for the BJT. So we call it R out or RO of the BJT. Only the BJT. Boom. And we can explain that very easily. If you look at this model, which is one of the models of the BJT, it's the pi model, and this is the T model. The pi model, to know the output resistance of the BJT here, what do? What's the first thing we need to do? Say the input is here, and the output is here. So this is the in, and this is the out. So how to find R out of the BJT? Or any amplifier, what do? What's the first thing we need to do?
Put B into 0.
Put what? B in there. It's not B. Put the input voltage to ground. That's the first step. Which is what she said is correct too. Put the base to ground, or just say the input voltage is grounded or 0. Okay? Alright? Once you do that, so this voltage is going to be what? 0, right? So that means the current here is going to be 0. Why? Because this current is the same as this one. So this voltage is 0, V pi is 0, V pi times GM is 0. This will be open, and if I put now here a current, it will go only through R naught. See? And that's why R naught is the output resistance of the BJT. You understand? Excellent. This is also part of the revision. Free of charge, of course. Next time, how many? 100 dirhams, everybody. Huh? I'll make fortune now. I'm helping you. This is extra work. I'm joking. All right. All right. Good. Good. So we also found the parameters RE and R pi. Alpha over GM for RE and R pi beta over GM. Good. That's it. Yani. We know beta and alpha relationship. Boom. That's it. So without further ado, boom. We'll go and start with the characterization of the amplifiers. 5 parameters. We have 2 resistance, the input resistance, output resistance. Then we have the open circuit voltage gain, the voltage gain, and the overall voltage gain. Okay? 5 parameters. Good. What does it mean, the open circuit voltage gain?
Without the load.
Without the load, yes. That's what it is. That means RL is equal to infinity. Or it is not there at all. Excellent. Very good. A big storm. We start with the first amplifier, which is the common-emitter. As you can see here, this circuit, is it in DC or AC? What's the first stage we need to study the amplifier?
AC.
So we have to make our circuit in AC domain, and it is now in AC domain, yes or no?
Yes.
Yeah, because simply this was actually VCC or VDD if you want, okay? Because it cannot make any circuit in here, any current in here, yes or no? Because this is grounded. But this is in AC, and in AC, any constant voltage becomes grounded. That's one more thing, is that the symbol here for the input signal, small. And actually that's probably why she said AC. Okay? Good. So the first thing is to make the AC domain circuit, or the circuit in AC domain. So then after that we put the model of the BJT. We replace our BJT with its model. We know where's the collector, where's the base, where's the emitter, and everything becomes clear. Good. So, and now we study Rn. Rn, we know the input voltage is at the base, and the output voltage is at the collector, yes or no?
Yes.
So this is where the output, and here was the input. That's it. Boom. And the common ground here is the emitter. Very good. So in terms of Rn, if you see here, if you send the current here, it will pass only through R pi, yes or no? So R pi is Rn, yes or no? That's what it is. And for R out, what do we do first?
We put VN
Vn to ground. If we put Vn into ground, that means V pi is going to be grounded, yes or no? And then once it's grounded, this is going to be 0, means open circuit, yes or no? Bye. And then we send the current from the output here. It'll go through this, you go through this, and that's it. So these two in parallel is the total output resistance, yes or no?
Yes.
And that's what it is. All right. We'll get to other stuff. So Rn is R pi, as we said just now, and R pi, we know it is beta over Gm. Very good. And it's actually, in terms of value, it's actually in the lower kilo ohms. So it's in ohms, in kilo ohms, but in lower stage. Okay? Very good. Now, this is R in and this is R out. It's already there. R naught parallel with RC. Now, the open voltage gain, AV naught, with no RL, yes or no? V out without RL over V in. As you can see here, V out, the voltage in here, is the voltage across these two in parallel, yes or no? So if I replace this in parallel, so we have the voltage across these two, is this current that goes out times this resistance, but it's going out of the resistor. That means the voltage is against this current, yes or no? There is a minus. So the voltage will be minus this current times this two in parallel. Good. By the way, let me ask you a question. Why, when I have a resistance, when the current leaves that resistance, the voltage that I have here, V, is equal to minus Ri? Why? Can somebody tell me?
Because it's
Wait, Henry, yeah.
because the current moves from positive to negative.
From high voltage to low voltage, go ahead.
Voltage, and by this direction it will be the opposite.
Exactly, exactly. Very good. So that means the current inside the resistance is going against the convention. It's opposite to the convention. Convention is actually, which is the reality, is that it goes from high voltage to low voltage, not from low voltage to high.
Yeah.
If it does so, there will be a minus multiplied by that current to make it in the conventional times R to make it Ohm's law. Good, excellent. Very good. That's we said that just in to remind, because sometimes some of you do some kind of these mistakes. So V out then is minus this current, which is GM V pi, times these two in parallel, divided by V in, which is V pi. Yes or no? V pi, this one. So V pi goes with V pi, and we have the remaining minus GM, these two in parallel. Okay? Good. GM is also equal to alpha. RE is equal to alpha over GM. Yes or no? So GM is going to be also alpha over RE. Remember, RE is equal to what? Alpha over GM. Yes or no? So GM automatically will be alpha over RE. Alpha over RE. That's it. And oops, there's a minus missing there. That's a typo. I'll fix it. Alright, alpha is almost equal to 1. Yes or no? So it's almost minus the total resistance at the collector, which is these two in parallel. Yes or no? Divided by the total resistance at the emitter. If I replace this model with pi model, with T model, I will have at the emitter only RE, yes or no? And that's the one in here. We'll come to see this again and again, okay? And finally, what we can say here is that, okay. Here, because RC usually is much, much lower than R naught, when these two in parallel, the winner will be the smaller one, yeah? RC then, So I can make RC parallel R naught equal almost to RC. And the total would be minus GM RC, which is that value. Alright, boom, boom. Now we get to the voltage gain. Now, for the voltage gain, that means RL is included. The same thing, and it's very easy to calculate it, actually, because here, instead of RC, I will have RC also in parallel with RL, because the load is at the collector, okay? So here I have another resistor. So in that case, all what I need to do, I can use AV naught, and instead of RC, I just replace RC parallel with RL. RC parallel with RL. That's it. Same, absolutely same formula, okay? And again, the same constant. The gain is almost equal to minus the total resistance in the collector divided by the resistance at the emitter. We'll come and see this. You cannot see it here in this graph because we are using the pi model. If you use the T model, you see what I'm talking about here. Now, last not least, is the overall voltage gain. This is the formula, which is basically the voltage divider multiplied at the input, multiplied AV. We studied this before, we are not going to waste our time. So the only thing we have to replace Rn with its value. Of course, here we have the source resistance, RC. No? Boom. So the input was what? R pi, so R pi over R pi plus R6, times this voltage gain. Boom. And that's it. We have also GM R pi. Remember, R pi also is equal to what? Is equal to beta over GM, yes or no? So when I have R pi GM, well, R pi times GM is going to be equal to beta, yes or no? Boom, and then that's beta. So, and here we have this divided by this, beta, this divided by that. As you can see here also, is actually minus beta, the total collector resistance divided by the total base resistance. As you can see in the base, here in the base branch, we have these two in series, yes or no? So the total resistance in here is going to be R pi plus R signal. You see? So you can see that the voltage gain or whether open or not, is going to be equal to minus alpha, the total collector resistance divided by the total emitter resistance, both. But for the overall voltage gain, okay, so for that matter, we have a different formula, which is minus beta, the total collector resistance divided by the total base resistance. Why we say these things? Because when we are familiar with the amplifier, I don't want to remember and do this all the time. I know just the resistance of the collector at the base or the emitter, then boom, I put them and I have the gain, that's it, okay? Just by looking at the numbers. So it's a way of remembering, okay? All right, good. Now what if I put a resistance at the emitter like we did in MOSFET? We put a resistance at the source. Why we did that when we did the MOSFET? We did that when we talked about the biasing. We'll come to the biasing of the BJT, okay? And we said that putting a resistance, which calls a degenerate source resistance. So that resistance, when you put it at the source, when you use MOSFET, stabilized the quiescent point. You make it stable, means that if there's any change in the threshold voltage, that change will not change the bias point, okay? We put it purposely there. And we call it the negative feedback, if you remember. All right? Here the same story, we put also resistance at the emitter to stabilize the operating point or the quiescent point. So let's study this. So again, we start with the circuit in AC domain. We replace now, instead of the pi model of the transistor, we use the T model. And we did not use the R0, which is the output resistance of the BJT here. Why? Just to make it easy to analyze it. The same way we did it for the common source amplifier, okay? So we took it off as good approximation. Good, so we take this circuit now and we study it. So for Rin, how much is Rin? So to calculate Rin, we have to divide the input, divide by IB, yes or no, because the input is at the base, okay? So this voltage divided by this, and let's calculate. So that's the Rin, so V input over IB, IB is equal to 1 minus alpha IE, is that true?
Yes.
How did you find that? Any idea? It's very simple actually. If you look at it, so IB is this current, yes or no?
Yes.
IE is equal to what? IE is equal to IB, yes or no? IB plus this current, yes or no? Alpha IE, yes or no? So from here, IE is equal to what? IB is equal to IE minus alpha IE, yes or no? Or 1 minus alpha IE. You got it? Solve the circuit. There's no need to memorize, okay? Did you get this equation? I repeat. The emitter current, this current at the emitter, is equal to this current plus this current, yes or no?
Yes.
This current is alpha IE, yes or no?
Yes.
And this current is IB, yes or no? I want to know IB, yes or no?
Yes.
So IB is equal to IE minus alpha IE, yes or no?
Yes.
So automatically it will be 1 minus alpha IE. Got it?
Yes.
You asked to repeat, that's fine. It's your right, yes or no? Good. So IB is equal to 1 minus alpha IE. Good? Excellent. Now the next stage is to find the relation between VI and IE because I need to cancel and do something. Now look at this. IB is much, much lower than IE. Yes or no? Yes, of course. Alpha is almost equal to 1. Yes or no? IB is almost equal to 0, if you see. Yes or no? This is IB, yes or no? Very, very small. Compared to what? Compared to IE. or IC. Very good. So then in this case, what I would say almost this one I can neglect, and I say this current, this voltage from here to here, which is the input, divided by this resistance will give me this current. Because I neglected this current, yes or no? It's almost zero, yes or no? So as if this current is due to this voltage across these 2 points. Got it? Very good. So IE then I can say easily is equal to the input divided by these 2 resistors in series, which is this one. And that's why I put in red. Understand? Good? Now it's easy. Bye-bye the input here, bye-bye here. And it's going to give me this. And this will go up, over. So this is my input resistance. Not done yet. Remember that alpha is equal to what with beta? Beta over beta plus 1.
Yes.
So that means 1 minus alpha is equal to what? So it will be beta plus 1 over beta plus 1 minus beta over beta plus 1. Yes or no?
Yes.
So this minus this equal to what? So this goes there. So 1 over beta plus 1. Very good. So here 1 over beta is going to be equal to what? It's going to be equal to this. Yes or no? So 1 over beta plus 1. So beta plus 1 will go up. Yes or no? Yes or no? And then it becomes here. Times this. Boom. Got it? So the input resistance here, when we look in the base here, is equal to beta plus 1 times the whole resistance in here. This resistance, we call it the resistance reflectance. Resistance reflectance means that whatever I put in here, resistance, it will be reflected at the input here by multiplying it by beta plus 1. Why? Because the current in here is equal to beta plus 1, the current that comes in here. Yes or no?
Yeah.
Got it? So that's why. Because the current here is equal to beta plus 1. This current. So therefore the resistance, whatever I have the resistance here at the emitter side, it will be multiplied by beta plus 1 to see the resistance that this input will see. Okay? That's what it is. It's a very nice feature. Now, let's compare our input resistance when we have RE, the big RE, when we have RE, and when we don't have RE. Yes or no? Which one? The one that we just did, yeah? So, the one with RE, we have it here. Boom. Without RE is equal to beta over GM. We just calculated it just now, yes or no? Without RE. Remember this? This is equal to what? This is RE. Remember the input resistance before was what? Input resistance is equal to, R pi. R pi was equal to what? The input resistance for the common emitter without RE, without resistance at the emitter, was equal to R pi, and R pi was equal to beta over GM, yes or no?
Yes.
Very good. So R pi, I can just replace it with beta plus 1. So this is R pi, sorry. So it's not RE, okay? So R pi is beta over GM. Yes or no? So this resistance divided by this, just by replacing GM and alpha and beta and everything, we can make this ratio, I'll calculate this, and we will find it finally is equal to 1 plus RE over small re. RE, the big one, is the one that we put. RE is the one that, small re, is the one that is made in from the BJT comes, okay? Doesn't come from outside the BJT. So this is ours, this is the BJT. Now, usually RE is quite small, I said, in the lower kilo ohm, like 1, 2, 3, 4 max, okay? So it's not high. So this RE can be high as much as we want. So that means the input resistance with RE divided by the input without RE is equal to 1 plus the ratio of our resistance compared to the resistance, the emitter resistance of the BJT. That's what it is, okay? This is how much we increased the input resistance in terms of ratio, okay? That's fine. And is almost equal to 1 plus GM RE, so this is, we are not going to dig into it very further. We just want to compare that the ratio, that indeed the input resistance has increased when we put RE. By how much? By 1 plus RE over RE, or by 1 plus GM RE. And we can get this from here actually, because RE is equal to beta, basically here it becomes alpha over, or what? RE is equal to what? Yeah, alpha over RE. Alpha over RE is going to be equal to GM, or alpha is equal almost to 1. So we can replace 1 over RE by GM. We get this. In any case, this is just a formula of that. Now we come to the next parameter, which is the open voltage gain. It's V out over V in without RL. Okay, good. So let's go back here and look at the circuit. So V out is equal to what? Again, look at this circuit. V out is actually this, the voltage in here. So it's equal to this current times this, but with minus. Yes or no? Very good. So it's minus alpha IE RC. What's that? Minus alpha IE, which is the current, times the resistance RC, divided by V input. Again, the input voltage in here is going to be equal almost to this current times these two resistances. This current IE divided by these two in series. And then IE get cancelled, and then we get minus alpha RC, minus alpha, okay, RC here, divided by these two. And again, here we have an interesting thing. You can see that the total collector emitter, the collector resistance is only RC, divided by the emitter resistance, which is RE small and RE capital. Okay, and exactly the same formula that we had before. Okay. And that's it. We can simplify this equation to get this. It's not a big deal. And the output resistance, again, is going to be the same as without RE, basically, because when we ground this, all this branch go bye-bye, and the only output resistance of the amplifier is going to be RC. For the voltage gain, again, when we include RL, RL will be what? Will be in parallel with RC, yes or no? Because the RL is going to be at the collector terminal, yes or no? So all what I need to do is get this formula and replace RC with RC parallel with RL. So without making the operations again. And again, the same story is the collector, the total collector resistance, which is the total, this one, parallel, these two parallel, divided by the emitter resistance, which is this in series. Of course, with minus alpha, alpha is almost equal to 1, so it's not a big deal. Now for the base, for the overall voltage gain, so it's going to be what? Again, we apply the formula, the whole formula, the voltage divider at the input and the output, times the open circuit voltage gain, AV naught. Okay? And basically what do we have? Rn we have it, yes or no? Rn we have this one. AV naught we have it also, which is this one. And Rout we have it, Rout is equal to what? RC. When you put all this together, you get this formula. And again, this formula, the same as the one that we just saw, is going to be the total collector current, the total collector resistance, which is RL and RC in parallel, divided by the total base resistance, which is going to be what? R signal, plus the input resistance. We said that the input resistance is equal to what? Beta plus 1 times the total resistance at the emitter. Yes or no? We just calculated it here. Okay, beta plus 1 times the total resistance in there. And then boom, that's it. Okay, the formula, it gets clear. Any question? Too much calculations, but if you just focus on it, become easy to understand. If there's anything I need to repeat, stop me, okay? Repeat or move on? That's good. Very good. If there's any question, please, All right. Boom. Now the next amplifier is going to be what? The common base. Very good. Now the input will be at the emitter in this case, and the collector will be our output. Boom. Okay. We replace the model of the BJT with the T model, and then we do the same story again. Very interesting. As you can see here, really, the input here is between the emitter and the ground, which is actually the same as between the base and the emitter. Yes or no? Because the base is already ground. Yes or no? Yes or no?
Yes.
That's it. You can see that this voltage divided by this current is going to be what? RE. Yes or no? Okay? But again here, there's no minus here. Because why? Because basically here, the current that is created here is the current by the voltage. It's not coming out of, out of the amplifier. That's why the input voltage in here divided by the current here is going to be RE, not minus. Okay? It's not minus. And the other reason also, the resistance can never be negative in this case. Okay? Okay, this is another reason. So you can see that the voltage across this resistance is the same as the Vin. So Vin divided by In is going to be what? Only that resistance, that is Re. This resistance. Which is, by the way, equal to alpha, alpha, right? Alpha over Gm. Now, let's go to R0. If I ground the input now to calculate the output resistance, so if this is grounded, this resistance is going to be between two grounds, so there will be no current. And this current here, which is equal to alpha IE, or is equal also to R pi, V pi being basically the voltage at the base, okay? And that one is actually equal to 0. So this current will be 0 also, making this branch altogether off. So the only resistance that the output current here, C, is only RC, okay? That's it. Now we go back to the voltage gain. So the voltage gain is equal to what? Let's calculate. V out without RL, okay? So there is no RL, so what is equal to? So V out is equal to what? Equal to this current that is created by the input, which is equal to alpha IE times RC, but because this current is opposite to the conventional current, so it's going to be minus alpha IE times RC. What is that? Is here. Minus alpha IE times RC. Now we come to IE again. IE, now look at this. Now IE is equal to, because here the current is going opposite to the voltage. So the voltage is going to be minus IE/RE, or IE is equal to minus VI over RE. Okay? Alright? So now minus minus is gone. Okay? And V out is going to be equal to alpha VI over RE times RC. So this voltage divided by this voltage, which gives me AV naught, is going to be alpha RC over RE, which is going to be this one. And of course, alpha over RE is going to be equal to GM, yes or no? So I replace that. So it's going to GM RC, exactly the same gain as the common emitter, but without the minus. Very good. Now, so that's it. It's the same. So there's no need to repeat. Now the voltage gain, of course, when I say the voltage gain and I be quiet, that means we include our load. Huh? Yeah. Our load, where we put it, is going to be at the collector. So that means it's going to be parallel to RC, yes or no? So RL is going to be there. So all what I need to do is take this formula for the open voltage gain and replace RC with RC parallel with RL. Boom. That's it. So again, GM is going to be alpha over RE, and we get the same formula here, which is the total collector resistance divided by the total emitter resistance. That's it. Multiply by alpha. That's not a big deal. Okay. So this has been seen before. And the overall voltage gain, again here, we can write it basically as the voltage divider at the input stage times the voltage gain, yes or no? So the voltage divider at the input is Rin over Rin plus R signal. Rin, we know is Re here, and R signal is there. So I just replace that, multiply by the voltage gain, which is GM RC parallel with RL. Boom. Now Re times GM again, Re times GM give me what? Alpha, yes or no? And that's why it's replaced there. So this is gone. So the remaining will be this divided by that. So this divided by that. Which is again the same result that we found before for the overall gain. Oh, but there is a, yeah. Here, yeah, that's it. That's it. This is, no, but here there's something really interesting in here. The overall voltage gain for the common base is different than the overall voltage gain in terms of here, in terms of how does it look like. The total collector resistance, which is these two in parallel, divided by the emitter resistance, which is these two in series. It's not the case for the common emitter. If you look at the common emitter, it's actually is equal to what? Is equal to beta, the collector, by the base resistance. So this is a bit different in the case of the common base. Okay? So that's it for this one. And last not least, the emitter follower or the common collector, which is a deja vu. We have seen it before. So here we have to have RL as part of the circuit. Why? Because without RL we cannot have any current that goes from the collector to the emitter. So RL here has two roles, has the role of biasing and it's a load as well. So it's a load for the circuit. So now let's calculate the characteristics. So Rin again is going to be the input voltage at the base divided by the current that is coming into the base. Yes or no? The input divided by IB. Now IB, we know how much. So again, we take this circuit. We are going to use this circuit because we replace the BJT with its T model, without having R out or R not. Okay. So here, as you can see, the emitter. Remember, the emitter IB. So let's remember IB. IB is equal to what? Is equal to
IC.
What's that? To make it easy, let's look at IE. IE is equal to IB plus IC. Yes or no? So it's equal to IB plus beta IB, yes or no? Because we know IC is equal to beta IB. Yes or no? We know that?
Yes.
Makes sense. So it's equal to what? It's equal to beta plus 1 IB, yes or no? So IB is nothing but IE divided by beta plus 1. Correct?
Yes.
Very good. So from here, again, we look at the input voltage. The input voltage is across this branch, and this current is almost zero, it's very small. So this voltage divided by these two resistances, again, we excluding R naught, we are using this model, not this one, I have to take it off. So this voltage divided by these two resistances in series give me the current in here, yes or no? So the current in here is equal to what? This voltage divided by this total resistance. So it's going to be V input divided by RE plus RL. Very good. When you have this divided by this, first you have to multiply this with this. And then this cancels this, and then everything will go up. And RE is going to be beta plus 1 RE plus RL. And it makes sense. Why? Because similar to the common emitter with RE, yes or no? So the input resistance is going to be beta plus 1 times the whole resistance at the emitter, which is in this case RE plus RL. Yes or no? So we have seen this before. So this is for R in. R out, very simple. When we ground this, boom, make it to the ground. Basically, this is going to be off because the input voltage creates this current. So this input voltage is to the ground. So this one, go open, by. So, and in the output resistance, do we put RL or no? Do we include RL?
Output resistance?
No, never. That's why we have to take off this as well. For R out. Never measure or calculate R out or output resistance with RL. We did this mistake before, yes or no? We don't want to repeat. Okay, good. So now when I send the current in here, it goes by only RE and then to the ground from the input voltage. Yes or no? So what is the resistance that I have? RE, that's it. Okay? Got it? Should I repeat?
No.
Clear or no? Clear, that's it. So RE is going to be R out. Very good, thank you. Now we go to the voltage gain. Now, before I go to the voltage gain, we call the common source, common drain or source follower. We gave it a name. It's a type of amplifiers. What we call them? We gave it a name. Voltage. We call it voltage.
Transfer.
There's a name for this kind of amplifiers. Voltage.
Buffer.
Buffer. Yes, yes. We call it voltage buffer. Very good. This is also voltage buffer, and it has three characteristics. Remember them very well. Voltage buffers, they have three major characteristics. Number one, they have the open circuit voltage gain is equal to 1 or unity gain. This is number one. Because they don't amplify the voltage, they keep the same voltage, yes?
The input voltage very high.
No, the input resistance, very good. The input resistance is very high, extremely high.
And the
As high as,
output resistance
and the output
very low.
resistance has to be very low. So three things. Input resistance high, output resistance low, and the open circuit voltage gain unity or unity gain, 1. When you say unity gain, it means 1. Okay? We are talking about the open circuit voltage gain in this case. Three things, huh? Remember that? Very important. I can ask a question anytime. Okay? We explained why. You can go to the video and also check that. We're not going to waste our time there. So we need to have these things in here. So as you can see, the input resistance is quite high, yes or no? Because beta is high. And we can make RL high because RE is low. We can make RL high to make the whole thing high, yes or no?
Yes.
We are good. What else? The output resistance is low. RE is low. Okay? RE is quite low. Very, very small. And if you want to check, RE is equal to what? Alpha over GM. Remember that GM for BJT is around 20 milliamps or 20 milliamp per volt. Yes or no? So if you calculate, this is almost 1 over GM. Yes or no? So it's 1 over 20 milliamp per volt, or 1 over 20 volt over milliamp, or 10,000 over 1,000 over 20 ohm. Yes or no? 1,000 by 20, so this will become 2. So 100 over 2, 50. So that's how much RE. RE is very small, 50 ohm. It's a joke. Yes or no? It's extremely a joke. So R out is quite small. Ah, yes, yes.
Can we ignore RE when we calculate? If it's
We shouldn't be. We should not. We should not. But we can, if that makes the calculation easier, or RE is compared to something big that we know, for example, R naught, for example, or RL that we know that's big. Yes, if we have the argument to neglect, sure, why, by all means, yeah. But just like that, ignore, no. We have to look. RE is with what? Okay, compared to R naught. Throw it away. Don't even take a chance. Throw it. R is very, very small compared to R naught. So it depends how RE is in the equation, compared to what. But if it is alone, no. Okay? Good. All right. So R in high, R out. Good. Now let's look at the voltage gain. The open voltage gain. Now to calculate the open voltage gain, we can do like the same way that we did with the common source. With what? No, with source follower, which is common drain. What we did, we calculated the voltage gain with RL, and we made RL go to infinity. Yes or no?
Yes.
Because that's easier. Because RL is part of the circuit. We cannot take it out. Okay? That's why if we take it out, we cannot calculate. The current, it must go somewhere. Okay? So RL here is a must. So the way to get around this problem is to keep RL and then for the voltage gain, and then to calculate the open voltage gain, the open circuit voltage gain, we have to make RL go to infinity, and we calculate it. So let's calculate the voltage gain with RL. So the voltage gain with RL is equal to what? As you can see, let's clean again. Okay, let's clean. Boom, 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 boom. Okay. So look at this. This is the output voltage. What is the output voltage? Is cross RL, yes or no? This is the output, yes or no? Very good. And the input voltage is where? Is this. We said that the base current is quite small, yes or no?
Yes.
So the ratio between V out and V in is what? What we call this kind of voltages? Voltage?
Transfer.
Divider. Voltage divider. Isn't this a voltage divider? It's very simple, yes or no? This divided by this is equal to this resistance divided by the whole thing, yes or no?
Yeah.
Make sense?
Yes.
Easy or not? Are you with me or not? I repeat. Voltage divider, you don't know what's voltage divider?
We know. We know.
Yeah, that's right. That means this voltage divided by this resistance is the same like this one divided by the whole thing, yes or no?
Yes.
So therefore this voltage divided by this is this divided by this. Clear? Okay? Good, that's it. So it's RL over RE plus RL. Now, this is the voltage gain. We're good. Now, to know the open circuit voltage gain, what do? We make RL go to?
Infinity.
And when RL goes to infinity, this ratio goes to where?
1.
1. Because we can neglect this, and this over this is equal to 1. That's it. So, the open circuit voltage gain is a unity gain. Is equal to 1. So, therefore, this is a voltage bump. Voltage bump. Okay? Good? Bingo, we have the 3 conditions verified. That's it. Excellent. Now the only thing remaining would be what? The overall voltage gain. Which is again, we apply the formula here. Is the voltage divider at the input times the voltage gain, or this times the open circuit voltage gain times the voltage divider at the output. Okay? Both formulas we can apply. We can apply this one. We have this already, we calculated just now. And we have this, Rn is equal to what? The whole thing. Put everything together, you get this. You can see that you can cancel this with this. Yes or no? So the remaining will be beta plus 1 times Rn divided by all this. Now we can cancel with this one, but I have to get this one over beta plus 1, yes or no?
Yes.
Yes or no?
Yes.
Good. And we have this formula. Now, because beta is quite high, and the input, the source resistance usually is small, so we can also neglect this, and we get Rn over Rn plus Re, which is what? Which is the same as, not exactly 1, which is the same like the voltage gain. We said that the overall voltage gain is the same as the voltage gain when the input resistance is high. Yes or no? That's what we found in the common source. Remember?
Yeah.
And it's true. The input resistance is high. Yes or no? So this is a proof that what we said was right. Yes or no?
Yeah.
Correct? Good? That's it. All right. That's it for this. And we are done with these amplifiers. So we go home. No, not yet. We have a summary. So let's go home then. Before we go home, let's look at the different amplifiers that we studied here. So these are the 5 characteristics of the amplifiers that we studied. R in, open voltage gain, R out, and voltage gain, and the overall voltage gain. Just a way of comparing. This row is for the common-emitter, this row with common-emitter with RE. You can see the difference here. Instead of RE now, we have RE plus RE, you see? For the input resistance. But when we increase the input resistance, we killed the voltage gain, the open circuit voltage gain. Because we have that gain divided now by a certain value that is above 1. So this is definitely less than that. The output resistance was the same overall. And the same thing happened with the voltage gain, AV, and all these things. The same thing in here. So instead of RE, we have RE plus big RE. That's it. This is number one. What else? For the emitter follower, you can see it's a nice high input impedance, low output impedance, and unity gain. Excellent characteristic for the voltage buffer. Okay? So this is just a summary of what we had studied. So before we go home, we finish the bias. We didn't talk about the bias, yes or no?
Yeah.
That's it. So no escape. You are going to stay here today. Oh my God. The teacher is killing us. Anyway. So for the bias, we have two conditions again. For biasing the amplifier, we have to make sure our operating point is in the active region in this case, and stable. Does not change when we change the BJT or the transistor. We said that, huh?
Yeah.
And remember the mismatch of the MOSFET and all these things when VT changed, blah blah. Same story in here. So we want to make sure that we have control of where the bias point need to be in the active, exactly in the linear region with maximum swing, and we want to make sure that that operating point does not change when we change the characteristic of the BJT, means where beta, for example, in this case, change, because beta is a big parameter here. From beta comes alpha, blah 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 blah, GM, etc. Okay? Very good. So this is the first way, is to fix the base voltage in here. And this is similar by fixing VGS. We said this is not good one. So the best way is to do what? Is to place an RE at the emitter here. Okay? We're not going to show you how that is, how to set the quiescent point, but I will show you how to make now the bias circuit, which is composed of these resistances, how to make sure that when we put RE in here, we make basically this amplifier, the whole amplifier, stable.
By replacing
By putting RE, because here we did not have RE. But when we put RE, as soon as we put RE here, this circuit becomes stable. But there's condition on RE. Okay, there's condition on the value of RE to make this circuit stable. Means the operating point does not change when beta change. To analyze that is very simple. We simplify this branch by Teflon. You know Teflon, right? Teflon, R Teflon.
Yeah.
Ah, very good. That's the one in here, which is basically these two resistances in parallel. Yes or no? Because this will become grounded, looking at this from here, so it's these two in parallel. Yes or no? Which is this resistance, RB. Then we do the following. We study the voltage, because we want to know IE, how IE is stable or not stable. So, to know that, we calculate what? We calculate the voltage on this path. So, the voltage from here to V, this voltage, which is VBB in this case, because we replaced, so it's going to be this VBB, is going to be equal to what? It's going to be equal to this voltage plus this voltage plus this voltage. Yes or no? Yes or no?
Yes.
The voltage from this node to this node, which is VBB, which is the Thevenin voltage.
Yeah.
So it's equal to this voltage plus this plus this. Yes or no?
Yes.
And that's it. Very good. Let's write that down. Got it. So let's write it. VBB is equal to what? Is equal to this voltage. This voltage is equal to what? This. Now the current is going in. Yeah, very good. So it's going to be RE, IE. Yes or no?
Yeah.
So, and this voltage is what?
Plus
Plus, yeah.
IB.
This voltage, I'm so talking about this. What's that voltage? VBE. That's it. VBE. Which is around 0.7 volt. Yes or no? Yes or no?
Yes.
So it's VBE. Because this is the base and this is the emitter. It's not here the emitter and base. No. This and this. Okay? So this is what? VBE. Plus this voltage.
IB, RB.
Very good. So it's going to be IB times RB. Yes or no?
Yes.
RB. Good?
Yeah.
Very good. Excellent. Now, what's the relation between IB and IE? We just said it before. IE is equal, or IB is equal? IB.
Beta plus 1. IE. Beta plus 1 plus beta IE.
Wait. Without memorizing, huh? Okay, let's see. So we have IE is equal to IB plus IC. صح.
IC equal.
But just a second. IB is equal IB. صح. IC compared to IB.
Beta IE.
صح. So IE is equal to what?
1 plus beta
So IB is equal to what?
1 plus beta IE.
No, IB.
IE
Over.
plus beta. Over.
1 plus beta.
Just a second.
IE.
Just a second.
We have IB and IE.
So IB is equal to this divided by this. Yes or no?
Yes.
When we bring this one down, it has to go below, sir.
Yeah.
I told you need a coffee today, right? Did I start this? I suggested that, yes or no? Now the coffee is needed. Yes or no? You deserve it. Very good. So IB is equal to IE divided by 1 plus beta. So I come here and I replace IB by its value. Yes or no? I'm lazy. I don't want to repeat. So I just write here plus IE over beta plus 1. Yes or no?
Yes.
We're good?
Yes.
Excellent. So now I have IE here and IE here. So what do? I bring this VB on the other side. Yes or no? I'm lazy again and I'm going to just throw it like this. Let's see. That's fine, I will repeat. Who cares? So here, so minus VBE, that was that side, is equal to IE RE plus this. Yes or no?
Yes.
Very good. Now IE, I can bring it together there, yeah? So from here, so this would be IE times what? Times RE plus RB divided by this. Yes or no? Yes or no?
Yes.
So now IE is equal to what? Is equal to this divided by that. Yes or no? So it's actually this equation. See? Okay? Good?
Yes.
Yes or no?
Yes.
Following me?
Yes.
You need coffee, yeah? I'm sure. Cappuccino or Americano. Excellent. So now we come to this equation. Usually VBE is actually smaller than VBB. Usually this one is in the 5 volt, this one is in 0.7, 0.5. So we can neglect VBB compared to VBE compared to VBB. Not neglecting, but it will not have too much of a change on it, okay? Plus or minus 0.1 volt, who cares about this? It doesn't make a big difference. But here is where to make IE really independent of the change in beta, so we have to make this one as big as possible compared to this, yes or no? So that if this change, it doesn't change the whole thing much, yes or no? Because RE is dominant. You understand? So that's the condition, is to make RE much bigger than RB over beta plus 1. This is the condition. To make now IE stable, which is condition. Because if IE is stable, the quiescent point is stable. Because quiescent point is dependent on IC, yes or no?
IC is stable.
Because
IC
from
is
IC
stable.
you get GM, you get... Yes or no? Okay? Good. So this is the first bias. Any question? Good. Alright. The second way of biasing, again, in the same story, that we use always negative feedback. The previous one also is called negative feedback. Okay? Now we come to this one, and the negative feedback, the same like in the MOSFET, is by placing a resistance between the collector and the base. Let's see how we make this bias constant, the same way. Same story, of course, we are looking at the currents, either IC or IE, but that's fine. To know the currents, I have to look at the voltage first. So now, the total voltage in here, before I go there, look at this current. The current that is here is not IC. This is IC. It's actually the one that goes inside the collector. This one is actually IC plus IB, which is nothing but IE. Yes or no? What comes in must go out. What goes around comes around. Okay? So what comes in is actually IC plus IB, and the same current need to go up. This is number one. Now, the voltage in here from the ground to VCC, because I need a reference, the only voltage I can really count on is VCC. So this whole voltage is equal to what? So I start from the ground. It's going to be equal to this voltage plus this voltage plus this voltage. Yes or no? Clear?
Yes.
Good? Very good. So this voltage is what?
VBE.
Very good. VBE. And this voltage is?
IB,
RB, IB. And this voltage is?
RC, IE.
RC, IE. Very good. Excellent. It's not IC.
No,
It's IC plus IB, that's IE. Ah, very good. Excellent. And the directions are fine. And we have that written here. Yes or no? Boom, boom, and boom. Good? Very good. Oh, what else? So we have IE, RC. Boom there. And IB, we just found it, huh? Is IE over beta plus 1. Yes or no?
Yes.
If it is IC, it will be IC over beta. Yes or no?
Yes.
Very good. So for IE, it's going to be IE over beta plus 1 and multiplied by RB plus VBE. So from here, we can get IE, common factor, and bring VBE on this side. So it's going to be VCC minus VBE over the factor that remains in here is what? Is RC plus 1 over RB over beta plus 1. Yes or no? Yes or no? We get this formula.
Yes.
Huh? Cool? Yes or no? Simple. Okay? The same story. To make now IE, so before we were talking about IC, yes or no? Here, because the equation gives me this, to make IE stable, I don't have to worry about VBE change, because VBE will not make a big difference because it's much smaller than VCC. I have to worry about this one. I have to make it as small as possible compared to RC. If there's any change in here, it should not change the denominator in here much. Okay? So the condition then to make IE stable is to make RC much bigger than RB over beta plus 1. You see? Good? So two different circuits, same concepts almost. But two different conditions here is to make here RC in this kind of biasing much bigger than RB over beta plus 1, and the previous one with RE at the emitter, basically that RE must be bigger than RB over beta plus 1. This one. This one. Yeah, RE much bigger than RB over beta plus 1. Tired. You had enough?
Yes.
Oh, Allah. Me too. This is the final slide of today's class, or almost the final slide. So in real life, to make an amplifier in the lab, especially in using discrete components, you have to have the amplifier isolated from the input and the output by capacitors. These capacitors will shield, will disconnect the DC components or voltages and currents here of the circuit of the amplifier from the DC values of the input voltage and the output voltage. We call these capacitors the coupling capacitors. Okay? And sometimes we can put a capacitor, like in this case in here, to make basically the emitter grounded, because the capacitor in high frequency, and that's the role, the capacitor in frequencies, in high frequency, in AC domain basically, they are short-circuited, okay? But in DC they are open. That's why they protect the DC voltage of these nodes from the DC voltage of the outside world. But in AC domain, means if there's an AC signal here, it will pass through. Now this capacitor, we call it what? We call it the bypass capacitor. Why bypass? Because it allows the AC signal not to go this path, but to go this path, because this capacitor in AC will become a short circuit. Okay? And that's how we do it in the lab if we want to make an amplifier. And that's it basically. So this is a summary for you to read and prepare for the final. We are not going to read that for you. But before we leave, we have to say goodbye, because this is the end of the course Fundamental of Microelectronics for the fall of 2016. But it's not the end of the game, you know. It's broken there, thank you very much. But the exit is actually next. So this is not the exit. The exit is when you finish, inshallah, in a couple of years, I think, or in 1 year. Good luck with that. That's when you get the exit. Until then, keep working. Thank you very much, and see you inshallah. Assalamu alaikum.